So remember, the F max is equal to, this is a basic quantity. That's what we're going to talk. That table, that's about all. It's not many parameters, something like a 4 parameter. You have to really manipulate that 4 parameter well, then you're not going to screw up when you do the analysis of digitized signals. And 3, 1 over delta t, all this stuff is right in the table, is equal to 2 times F max, and which is called, I use lowercase f or uppercase f, really doesn't make any difference. This is called the sampling frequency. Sampling frequency is twice of the maximum frequency in the analysis. This is all proved by Shannon's theorem. Why need twice of F max? To capture the meaningful the data. And one last parameters is delta F. Delta F is 1 over T. Another one which belongs here is total time is equal to, of course, n times delta t. So you can take this out. This is really electronic machines when you deal with, that's what 2 to the n power is total number of storage. So t is equal to n times delta t. F max is half of the n times the delta f, and fs is equal to 1 over delta t, or delta f is equal to 1 over t. This is the kind of the digital processing rule. Of course, there is a theorems behind it, and so on. And as I give you like this, t is equal to, this is all coming out of these 4 parameters. T is equal to 1 over delta f, same as this. Okay? Or Fs, sampling frequency, is equal to 1 over delta t. T, of course, t is equal to n times delta t, and Fs over here is equal to n times delta f. Of course, over here, Fs is equal to twice of F max. It's just to write the same thing in different way, but okay, let me give you some quick example to get the feel of it. T 1 over delta F to get the feel of it. So I'm going to choose, example, I'm going to choose the delta F 5 Hertz. In the shock analysis, which I'm always involved, 5 Hertz is too big, okay? But for vibration problem, of course, 5 Hertz may be acceptable for many different cases. So here's a 5 Hertz, and N is 1024. Typical, the dynamic signal analyzer with lower price range, number of data point it can handle is 1024. 1024 is 2 times what? I forgot, that's why I'm asking. 10? Is it correct? Is it 10? 2 to the 10 power. Okay. Then what's the total time? Then if you said this, then the following quantities are automatically determined. Okay? What's the total time? Total time of record. Then you will analyze it. Fourier analyzer. Fourier analysis. It repeats the same block. Okay? It repeats the same block because T is constant as you set this up. So what's the total time? What's the equation for total time? It's given is 1 over F. So total time, let's take a look at it. Total time, this is available. Okay, so what else is available? Total number of data point is available. Okay, so T is equal to 1 over delta F, which is equal to 1 over 5 is a 0.2 second. It carries a 0.2 second. It's automatically determined. What about the sampling frequency? What about the sampling frequency, Fs? Fs is n times delta F. Take a look at this there. What about F max? Which is half of the Fs. Fs is equal to 1024 times 5 is equal to then this becomes half of those is 2560 Hertz. So it's just this is delta T F max, delta F, capital T. This is basic 4 parameters. So then you choose these parameters. Then you can determine, for example, F max. F max is 1 over 2 delta T, 2 times F max is sampling frequency, Fs. Fs is equal to 1 over delta t. Delta t is 1 over sampling frequency, vice versa. So it related to also t. T is n times delta t. Delta t, the delta f is 1 over n delta t, because n times delta t is the total time t. So it just relate. This is basic quantity. It relate by the 4 parameters. This n is data block size. Is e to the n power. It's always, because it's on and off business. Okay. So take a look at this closely. So this table is when I conduct the measurement in the lab, I have this right on the wall, and always look at the relationships. Okay. So you might need this table tonight, this evening's exam, as I recall. So you might have to use this table, which means one problem, not heavily related, but somewhat related. So it's all open book, so you can just use it. Okay. Another couple of problems I'm gonna use it to show you. Then we'll move on. So let's say, well, in my analysis, I need to include maximum frequency as 50,000 hertz or 50 kilohertz. Okay. So 50,000 hertz is really, really high. For your ear, how many hertz do you think you can recognize it? So violin has a very low frequency to high frequency. Baby crying, somewhat high frequency. But just the rule of the thumb, what's the range you can hear in your ear? Ear cannot recognize 50,000 hertz. It doesn't recognize. You can hear nothing. Okay. So what would it be? Anybody took the acoustics course in ME? Like, what would be the range? It's about 10,000 hertz is what you can recognize. Okay. So, but let's say it's at 50,000 hertz is what I want to know. And the delta F is equal to 0.0001 hertz. 0.00. Then question is, what would be the sampling frequency? And what would be the number of data points? Can you tell? Fs. If its F max is 50 kilohertz, sampling frequency is twice of that, which is 100 kilohertz. What about the total number of points? If you look at there is Fs we know, and we know delta F, which is equal to 100,000 hertz divided by delta F 0.001 hertz. So you have 10 to the 8 number of data points. using analyzer. You can carry HPC in the field. You can. So 10 to the 8, which is about 100 mega point, which is a lot. You can deal in the lab. It's just impossible. Of course, HPC you can just do number crunching right in there. You can solve. So in this case, you want to have a total range of frequency is from 0 to 50 kilohertz. Then I love to have a delta F 0.001 hertz. Then you don't, what your idea is, I don't want to miss any peaks between the frequency point. Then that means as I look at such a person, he doesn't have any feel. Usually fresh graduate, if let's say if I ask him, fresh graduate, to make a FEM model, he will, you know, this is real. This is not a joke. It has a chain, you know. It has wheels. It's like this. Then I said, well, make a finite element model. Then he's so anxious, and he made a model so precise, so defined the elements so well. For example, he can put so many fine elements. It's just impossible. You just spend the day and night, weekend, and no time to play soccer. Just then he brought that to me. He doesn't know what he's doing. Does he doing a static analysis? Does he doing the dynamic analysis? What he wants to capture? Same thing. All of my students, one time or another, you have to build a model. Build a model without the direction is a total disaster. Because this generates, first of all, number of data points which you can't just impossibly handle. You can't just do that. And what you want to do, dynamic behavior you want to really find out, then you don't need all this refined modeling, right? Do you need just to capture the basic mode with the corresponding frequency, which is much lower? Then you do not need this. So you have to. That's what the engineer is supposed to do. All the judgment is what you have to do. So that's your responsibility. 50,000 hertz, you may not need 50,000 hertz. 50,000 hertz is really in the acoustic range. It's not for equipment range, acoustic range. So mechanical engineer may not need 50,000 hertz. But analyzer, nowadays we are dealing with, they have a capability to deal with the 50,000 hertz. More expensive. So you have to, you can't just demand everything. You have to give up something. Okay. Let's see which one I should give you. Yeah. Y power of 2. Why 2 to the something? Or 2 number of data point is 2 to the some power. I said just to put the n. 2 to the n power to make like electronic gears and all that, because it's on and off. Electronic gears, all it has is light is on or light is off. So that's the 이진법. That's the only way to recognize. But when you're dealing with a computer, HPC, and all that, then you don't have to stay right in. It could be higher than the given number, 2 to the n power, and that number could be higher. The higher is okay. Higher is okay, but it's 2 to the n is a stopping point to manipulate using electronic gears. Otherwise, you can't, because n is 1, which means you have just on and off 2 lights, 2 light bulbs. If it's a 3, then that's a 8 light bulb, vice versa. The conversion you can do. And you can convert into this guy. You can make it 2 to the something, may not be exact. Then could be, you can add a number. But in the HPC, such a computational computer, then you can make it exactly like this, but you can add more. Then then in the computation process, it meet the requirement, has to be larger, not the smaller. But this requires 10 to the 8th power, the storage point. If it's larger, more space, more storage, it's okay. If it's less, it's a problem. Because to manipulate the data, it requires 10 to the 8th. So if it's less, then it's less than requirement, then you can compute with accuracy. That accuracy. So, so you have to increase, but which is ridiculous. That's what I'm saying. This is ridiculous storage requirement for hardware. For computer, fine. But you can't carry. Nowadays, even computer itself is really small. So nowadays, its problem is really slowly disappear. Because all the days, like a tabletop PC, all the days it takes about 2 or 3 rooms to accommodate the hardware, but nowadays it's not. So it's getting better. Okay, so a little bit talk on the digital computation. If you look at this, how many of you really saw the dynamic signal analyzer with the scope in there? With the scope in there, you could see rear. This is really scope in the dynamic signal analyzer, and this is another scope. This is another scope. Usually they have a button to change the position, but if you look at it carefully, it has a 3 axis. This is rear, this is imaginary. When you take a Fourier transform of the real data, it has a real part, it has an imaginary part. If you look at straight through this axis, this is like a frequency axis, and this is real, this is imaginary. So if you look at the straight into the frequency axis right here, then that's a complex display. And if it has a mode and all that, it has shape is like a circle. Sorry, I can't show you, but I keep saying maybe next year. And in the imaginary axis, it's really imaginary along the frequency. It's like a Fourier transform. Fourier transform, and it is imaginary part and frequency. Another word is like this. Keep going. So it has a real part. X is like a real part, because X is X real part minus J X imaginary part, right? Or this is equal to X e to the minus J 2 pi F T, like this, right? Real and imaginary part. So this could be a real, X real. This could be X imaginary part. Another way you can do is this part is real, this part is imaginary, this is a magnitude, and I could do just the theta, magnitude and phase. So you can have magnitude and the phase. So usually this comes like this, depend on the number of the mode or resonancy. And as you saw there before, possibly, and you can have usually if this is a mode, then it has a sudden drop, something like this, okay? Or in general, right at the resonance, it comes right here, and this is the point, the phase is shifting drastically. So you can do that. And this is called the Nyquist plane. The Nyquist plane, Q-U-I-S-T, something like that. Nyquist plane. It has looking into straight the real and imaginary part. I have a booklet, very nice booklet from Hewlett-Packard. It is taken all from there. Anybody want to know detail, you could use that. Over here, B is the same as F max, but Bandet's book uses the B for that, and all this is covered by the table t is equal to n times delta t. And this is f max. Okay. So 2 times f max is equal to fs. Fs is equal to 1 over delta t. So notation here is based on that booklet, but it's really same. Delta f is the same. Okay, next one, I'm going to just comment on this. If you look at the signal processing book, but circular effect is not a big problem for any signal processing equipments because they take the number of data set as twice of the number of data set required for a minimum computation. So, but I want to mention this just to make sure what this is. Circular effect. When you take a Fourier transform of any data, it just has the finite data, finite number of data. So, for example, if you have, this is a t, if you have a signal coming into it, then take the total t, then assume it repeat that amount of the data set, and next one will be identical like this. So 2t, something like that. So it has a finite length of the data set. Then after that, it's just assume the repeat is coming after. So 2t, then it could be 3t, so on. But if you look at the, for example, the autocorrelation function, this hat is estimate. So estimate of autocorrelation function, then this is equation set t minus tau range rather than t for the finite the record of the data set, and this is the cross correlation function, and this is estimate. It's still same. The range is t minus tau. The problem is this. Well, this is getting the autocorrelation function using inverse Fourier transform. This is inverse Fourier transform. And let me go down to this first. I'm going to first go through that, explain. Then we're going to look at that. I'm gonna just draw maybe from here to here up to maybe here. Okay, 2 period. It just repeat by itself. So I'm gonna cut one cut here. I'm gonna cut the same block, because to get the Fourier transform, it could be just, I'm gonna just draw like this. Could be here. And to get the Fourier transform, it assumes the same block is coming, repeat, for the t, for the 2t, and so on. So you're gonna have like, it's the same, okay? Then it could be like whatever. You need a 2 point to get the r xx tau, which is really e to the any arbitrary point xt1 plus tau. So if you get like the definitions, T1. So here first I'm going to pick up the T1 would be maybe this point is T1. So I pick this point. Then tau plus the tau. If tau is within the T, if tau is within the T here, tau, that's okay. We can just process as we are doing it. But problem is in the process, if this comes right here, this is tau. So this guy is a T1, but this guy is T1 plus tau. Okay. So this is T1 plus tau, but the Fourier transform takes from 0 to capital T, and after that it repeats the duration of the data and repeat the same T. So which means, okay, so this portion of the data, they recognize as a beginning of this data. This much goes right there. Because all it recognizes is the total duration time of capital T, then it just repeat in the Fourier transform computation. When tau goes beyond, beyond the total time T. So, okay, then what's the time length here? This duration is same as that duration. So this is people call the wrap around the arrow. Wrap around the arrow means this is like a 0 to T. So wrap around, if the data spells out up to here, T1 plus tau, it just goes around here. Goes around, wrap around. It's called, some people call the wrap around arrow. So this data, this is what? This is T1 plus tau minus T, isn't it? So now this is same span. So this is T1 plus tau minus T. So now it takes that point and that point, rather than this point to that point, it just take this point as this guy, and then next to take this point as that guy, which is called the wrap around the problem. And let's see. that generate the arrow. What arrow? And that, if you do this guy, when you compute that from here to here is t minus tau. You compute this point, take away that point, it should be t minus tau. So this point is what they are using it, which is not true because of the wraparound effect for Fourier transform. That's what end up to compute. So instead of this, you got you end up computing that kind of the two-term equation, and which generate this type of the shape for this is autocorrelation function, which is not true. It has a reflection part into it. This is really forward, and this is like backward. So idea is, which is wrong. So idea is, if you generate time span of the 2t, then conduct the Fourier transform, then you can expand in the time domain, not just to put it together, one and another one, first term and second term in the previous page, then you can just delete the second part, then this is what exactly the autocorrelation function for any general signal. That's the whole idea. I didn't talk very well. I know. Usually when a teacher talks, some area is... so then remove this part just to keep the first part, which is up to the time t for autocorrelation function. So this part is really due to the wraparound effect, because the same thing, just rolling around. So that's all I want to say. But any instrument, they take always more than one span of time. So you will never see a wraparound effect or called the circular effect at all. Okay. So that's all I want to comment for the wraparound problem. And this is all coherence function we covered the last time. And we will talk quite a bit from Wednesday about the gamma xy squares and so on. So this is in the book, Bandet's book. So you can look at a lot more in there than what I really explained. So, but do that. But just understand there is a circular effect in the data processing, which is really same as wraparound effect, because of the block of the time data to analyze is just to repeat by itself. Okay. All right, I think we have to leave, and I'll see you tonight at 6 o'clock. Then Higgy will take your exam paper back at 8 o'clock. But if you finish early, then just to take it up to Higgy. Okay? All right, we'll see you.